of geometrical shadow, that is known as diffraction. Then we had seen two types of diffraction. One was Fresnel's and other one was Fraunhofer's. If the separation between source slit is finite, then we get Fresnel's, and if the separation is infinite, then we have Fraunhofer's. Then we had seen diffraction at a single slit, where D is the separation from the screen through to the slit. And this yn, what I have written, is the linear separation. So all the secondary wavelets going across the slit AB, these are focused at the central point of the screen, this point O. And the wavelets from any two corresponding points of the two halves of the slit reach this point in the same phase and add constructively to give us what? Central bright fringe over here. Then at this point, P point, we get our first minima. Similarly, we'll be having a first minima over this side. So we have calculated, we had seen, this was the, A was the width of the slit. A is the width of the slit. So conditions for nth secondary minima. For nth secondary minima, path difference is n into lambda, n multiplied by lambda. Yes, right. You are right. It means that only. So sine theta is n lambda by A. And no, in that case, the waves add destructively. So this we'll discuss later today only. Then it will get clearer. So A sine theta is equal to n lambda, and according to small approximation, the angular separation came out to be n lambda by A, and the linear separation was n lambda capital D by A. So capital D is what? Capital D is the separation from the slit and the screen. And A is what? What is A?
Slit width.
Slit width of the slit. So this was case for minimum. Let's see the condition for nth secondary maximum. So in case of nth secondary maximum, the path difference was 2n plus 1 lambda by 2. So on applying small approximation, angular separation came out to be 2n plus 1 lambda by 2a. And the linear separation. Linear separation means this only. This is the linear separation, and this is the angular separation. The angle that this linear separation is subtending at the center. This is known as the angular separation. So for the case of secondary maxima, we had seen that linear separation is 2n plus 1 lambda capital D by 2. So let us do some numericals to just clear this top. See, it says a parallel beam of light of 600 nanometers falls on a narrow slit, and resulting diffraction pattern is observed 1.2 meters away. It is observed that the first minimum is at a distance of 3 millimeters from the center of the screen. Now we have to calculate the slit width. Now, what is the wavelength given?
600 nanometers.
In terms of meter, what it would be?
600 into 10 raised to minus 9.
Minus 9. So it would be 600 into 10 to the power minus 9 meters. And capital D, that is the separation from the screen. So the separation between slit and the screen is what? 1.2 meters. Now the linear separation is also given to us, that the first minimum is at a distance of 3 millimeters. This means if this is the case, then it is saying that if this is our first minimum, then it is at a distance of 3 millimeters from the center of the screen. So it means it has provided us with y, that is the linear separation. So 3 millimeters is for the first minimum. That is y1 will be 3 into 10 to the power minus 3 meters. Now see what is left. A, which is the slit width. Now see, for the case of first minimum. See, this was the linear separation for minimum case. Now if n is 1, if I put n equal to 1, so y1 will be 1 multiplied by lambda d by a. So what will be y1? Y1 will simply be lambda capital D by a. Why am I using this only? Because it has specified that we have to calculate for minimum. So if you put it in this formula, that is y1 will be equal to lambda capital D by a. From here, if you take out the value of a will be lambda capital D divided by y1. So let us put all the values of a. Lambda is 600 into 10 to the power minus 9. D is 1.2 and y1 is 3 into 10 to the power minus 3. So on solving this will be 200 and this multiplied it will be 2.4. So A will be 2.4 into 10 to the power minus 4 meters. Is it clear?
Yes, ma'am.
Okay, so just note down the question. We'll do more numericals. Just note down the question in the solution. And if you have any doubts, you can ask me. No, only Fraunhofer's diffraction is included in your syllabus. No, Abdullah, there are different formula for Fresnel's diffraction. That is, I think, deleted now in your syllabus. Earlier it was included. Now you have only Fraunhofer's diffraction.
Okay.
Done?
Yes.
Let's see some more numericals on this. Okay. See, it says in a single slit experiment, light of wavelength 6000 angstrom is used. Slit width is provided to us and the separation of the slit and screen is given to us. Now it is again simple formula based question. The first part is asking us the separation of first secondary minima from central maxima, angular as well as linear. So angular separation and linear separation for first secondary minima. So angular separation is what? N lambda by A. That's what we have seen. Now for the first one, let us put n equal to 1. So theta 1, that is angular separation for first secondary minima, will simply be lambda divided by A. Lambda, what is the wavelength given? 6000 angstrom. How do we convert angstrom into meters?
Multiply 10 to the power minus 10.
10 to the power minus 10. Yes. So it would be 6000 into 10 to the power minus 10. And this is given as 2 millimeters, the slit width. So it would be 2 into 10 to the power minus 10. So theta 1 will come out to be 3 into 10 to the power minus 4. And it would be radian, as it is the angle. Now it's not only asking us the angular separation, it is also asking us the linear separation. So linear separation is y. Y will be, you can write all these things and multiply it with, like for n, how do we write? N lambda by a multiplied by d. Now we have the value of this. So we can simply multiply this term by d and get the answer. For n equal to 1, y1 will be lambda capital D by A. Now see, what is the value of lambda by A? Lambda by A is 3 into 10 to the power minus 4. And capital T is given 2 meters. So we can simply multiply it by 2 and y1 will be equal to 6 into 10 to the power minus 4 meters. So this is the angular separation and this is the linear separation. First part is clear to all of you?
Yes, ma'am.
Yes, ma'am.
Now see, the second part is asking secondary maximum, but this time we don't have first. We have second secondary maximum. So this is also formula based question only. Instead of n equal to 1, this was for first part, this is for second part. Now see, theta n for secondary maxima, check up into your notes. It is given as 2n plus 1. This time it is not only n. For case of maxima, it is 2n plus 1 lambda divided by 2. So now the value of n is what? What should I write in place of this n?
2.
2.
Because secondary maxima is asked. So theta 2, it would be angular separation for the second one. So it would be 2 multiplied by 2 plus 1 and then lambda by 2. So this gives 2 multiplied by 2 is 4 and 4 plus 1 is 5. So theta 2 is 5 lambda divided by 2. Now see, rest of the things we are aware of. 5 multiplied by lambda, lambda is 6000 angstrom. 2 multiplied by a is 2 millimeters, 2 or 3. A is 2 millimeters. This is 2 into 10 to the power minus 3. So this will be 4, 5 and 6, 3. So it will be 7.5 into 10 to the power minus 3. Similarly, you can double it. You can multiply it by d. So it will be double of this. And you will be getting the linear separation. Second part is clear?
Yes, ma'am.
All right, just note it down.
Yes, ma'am.
Done?
Yes, ma'am.
Now, let's see another numerical, one last numerical based on this concept only. How to calculate minima and maxima. So it says a parallel beam of light of wavelength 600 nanometer is incident normally on a slit of width A. So we don't have the value of A, we have to calculate the slit width. So distance between slit and screen is given as 0.8 meter, and the distance of second order maximum from the center central maximum only. This is given as 15 millimeters. We have to find out slit width. So see, which formula should I use? Maximum formula or minimum formula?
Maximum.
Maximum.
Maximum, because it has given us the value of linear separation for second order maximum. So yn is what we have just seen, 2n plus 1 lambda d divided by 2a. Now see, tell me terms one by one. Sanya, you tell me what is lambda? Yes, Sanya. Anyone else? Okay, she has given, okay, 600. 600 nanometer. So lambda is 610 multiplied by 10 to the power minus 9 meters. All right, Mariam, you tell me, what is the value of capital D? Yes, Mariam, at least write it in the chat box. What should I write for capital D? Anyone else?
Yes, ma'am.
0.8 meters.
0.8 meters, because capital D is what? It is the separation between slit and screen. So capital D will be 0.8 meters. Now see, A we have to calculate, and Y2 is given to us. That is 15 millimeters. For the second order maximum, it is given as 15 millimeters. So it would be 15 into 10 to the power minus 3. Now see, since it is given us second order, we'll write n equals to 2. So Y2 will be, again, this is similar to the previous one, plus 1 lambda by d by 2a. So Y2 will be equal to what? 5 lambda capital D divided by 2a. Now see, all the terms you are aware of except for this a. So a will be equal to what? 5 lambda capital D divided by 2y2. If you just transport it this side, so a will be equal to 5 into 600 multiplied by, how much is your answer coming, Abdullah? 80 into 10 to the power minus 6. Correct. Yes, right. So it would be 600 into 10 to the power minus 9 into 0.8 divided by 2 into 15 into 10 to the power minus 3. So as rightly answered by Abdullah, the answer is this will remain 0.8. Rest of the terms will get cancelled. So it would be 0.8 into 10 to the power minus 7 meters. Clear to all of you?
Yes, ma'am.
Yes, ma'am.
So for all those who have not written it down, just note it. Completed? Okay, see that let us calculate that width of the central maximum. See, width of central maxima is basically the separation between two consecutive first order minima. Like if I say this is the first order minima and this is the first order minima on its lower side, lower to the central maxima. So this part in the center that I'm getting, this is known as the central maximum that we have seen. So let us see what is the width of this if you specifically have to calculate the central maximum. So the angular width of the central maximum means whatever angle this central maxima is
Previous question.
subtending on the center. Yes,
Ma'am, can you take the previous question?
previous question, this one.
Yes, ma'am. Ma'am, the power would be -5, right? 0.8
Then
into 10 to the
the
power
power,
-5.
this is 30. This will be 300. One will get cancelled. Yes, yes, yes. Yes, in terms of 80 also you can write it as 80 into 10 to the power. Fine?
Yes, ma'am.
Okay, see. So I was telling you the angular width means the angle that this central maxima is subtending. So if it is θ1 from this slit coming and θ2 below, so what will be the total angle subtending? That will be just θ1 plus θ2. And see, both these angles are equal. Like if this is θ1, then this is also θ1 only. So angular width of central maxima, this will be twice of θ1. So this is given as 2 lambda by a. This is the angular width of central maxima. And specifically, you have to calculate the linear. Means this y1 plus y2. Then the linear width of the central maxima is what? Angular width multiplied by d. D is what? D is the separation from the slit and the screen. This is the screen. So linear width is given as 2 lambda d by d. So these are just two formula. Just note it down. This is regarding the width of the
Ma'am,
center. Yes,
width is the distance between two minimas.
yes, two minima. See, because distance between these two minima will give us the distance between the central maxima only, the length of the central maxima only. And if we have to calculate the angular, then it would be whatever this is subtending at the center. So that will be just twice of this theta.
Ma'am, if we instead of first minima, if we use first maximum, will it be correct?
What?
Instead of first minima, we use first maximum.
If we get the first maximum, you can use first, then it should have been, it would be first maxima above this point O from the central part on the screen and first maxima below also.
Okay.
But what happens is that all the light that is coming, the secondary wavelength, they produce a central bright fringe over here. What are fringes and details you will be learning in interference. So what happens? Once bright one is over here, then we'll be getting darker ones, dark fringe over this side. So that's why I have written first minimum. So alternate bands of light will be getting. Completed. Shall we move forward?
Yes, ma'am.
Yes, ma'am.
Okay. Let's see, one topic is left, that is intensity distribution curve. See, before understanding what is the graph between the intensity and the wavelength, if we plot a graph between intensities of maxima and minima against the diffraction angle, then we'll get a certain type of graph that we'll see later. Now see, for minima, the path difference is n lambda, as I've told you. And for maxima, it is 2n plus 1 lambda. So for first minima, n would be equal to what? N will be equal to 1. So path difference would be simply lambda. Similarly, if this is the case for maxima, it would be 3 lambda by 2. Then if we have second minima, means after first minima, if we take second minima, n would be equal to 2. This would be 2 lambda. Similarly, n equals to 2. This becomes 5 lambda by 2. So this keeps on going. Lambda, lambda by a, 2 lambda by a, 3 lambda by a, 4 lambda, 5 lambda by 2. All these ratio will keep on moving as I'll increase the number. Like if this is for n equals to 1, this is for n equals to 2. If I take it for n equals to 3, this will be 3 lambda. So when we plot the graph between the intensities of maxima and minima against the diffraction angle, we get a graph of this type. So it has a broad central maxima in the direction of incident light. And on either side of the central maxima, it has the secondary maximum of decreasing intensity, as you can see. This all is done experimentally. So can you see the difference in intensity? There's a decrease in the intensity. So it has secondary maxima of decreasing intensity at these positions. And see, all these intensities, I by 21, I by 61. So basically what has happened, the intensities of the secondary maxima relating to the intensity of the central maxima, these are in the ratio of 1, then 1 is to 1 by 21, then 1 by 21 is to 1 by 61, 1 by 61 is to 1 by 121, and so on. So intensity of first secondary maximum is just 4% of the central maximum. Now see, intensity of secondary maxima decreases with the order of maximum. What is the reason? Why is this intensity decreasing? What happens is that the intensity of central maxima, the central maximum, is due to constructive interference of wavelets from all the parts of the slit. The first secondary maximum is due to contributions of wavelets from the third part. That we'll see just few minutes later on. That why do we get constructive? Why do we get maxima? Why do we get minimum? But the reason is just because of the constructive interference of wavelength from all the parts. So what happens? Intensity of secondary maximum keeps on decreasing in the increase in the order of n. With the increase in order of n. As the n increases, the intensity decreases. So just write down this also, and this keeps on increasing. As you will increase n equals to 3, then you'll write n equals to 4, n equals to 5. More the graph will keep on decreasing. Like this. Will keep on decreasing. So just note down these 2 points. Then we'll see why do we get maxima and minima.
Teacher, not done.
Should I scroll it down?
Yes, ma'am.
Ma'am, done.
Plotted?
Yes, ma'am.
Okay. Now see let us see why do we get maxima, why do we get minima. Okay, before that, one more thing. See, just note down this, what happens if this is a wave. This is the amplitude of the wave and the portion that we get above the bulging part. This is known as the crest. From your basic knowledge, you all are aware of this. And similarly, this part, this is again the amplitude, this part. This is known as what? Any idea?
Trough.
Tough.
Trough, exactly. This is known as trough. So when this kind of thing happens, when this kind of wave adds up with this kind of, means one crest adds with a trough. So what happens? This results in destructive superposition. This is what is known as destructive superposition. If this is added. So if path difference, see, is lambda, then the path difference becomes lambda by 2. And if you ever see that path difference is lambda by 2, just remember that what kind of superposition it is. It is destructive superposition. So this is just a very basic concept. Let us see through two questions. Like why path difference of lambda results in minima. Why do we get minima? See, the rest of the explanations I've already written. You can note it down, just understand it first. So to understand it, we can divide the slit. Let's say, let's name it as AB. So we can divide this slit AB into two halves like this. So if width of the slit is A, what will be this part, this much part?
A by 2.
A by 2. And similarly, this part also will. be a by 2. All right. Now see, then the path difference between the wavelets from this and this will be lambda by 2. So this will be lambda by 2 and this will be lambda by 2. So what happens, as I've told you just now, that whenever lambda by 2 is the path difference, what kind of interference or what kind of superposition do we get?
Destructive.
Destructive. So what happens? The wavelets from the two halves reach this point on the screen in opposite phases. So that's why they interfere destructively so as to produce minimum, or you can say a minima. Because what happens? Lambda is the wavelength wave given to you. Wavelength is lambda. So we have to choose, we have to divide this in such a way that why have we taken only two divisions? Why have we divided into only two parts? Because we have to divide it in such a way that we get lambda by 2. So lambda can be taken only, we can divide this in two equal parts. Similarly, if you see, when path difference is given to you as 3 lambda by 2. So see, if we divide the slit into 3 equal parts, let's say this is the slit, this is the slit AB. Now see, if we divide it into 3 equal parts, again, A is the slit width. Then what will be this part only?
A by 3.
A by 3. This will be A by 3, this will be A by 3, and this will be A by 3. All right. Now see what will happen. The path difference between two corresponding points of the first two parts will be lambda by 2. So this till over here, this is similar to the previous case as we have seen. In the previous question as we have seen. So this will be lambda by 2 only. So the wavelets from these points will interfere destructively. But see, this is left. However, the wavelet from this third part of the slit, this will contribute to some intensity, and that's how it forms the secondary maximum. So the intensity of maximum is much less than that of central maximum. Is it clear?
Yes, ma'am.
So just note it down. From here, I believe you have plotted the graph, the intensity distribution curve.
Yes, ma'am.
Done.
No, ma'am.
Yes, completed.
Yes, ma'am.
Yes, ma'am.
Okay, so this brings us to the end of the topic, diffraction. I think sir has joined us. He'll continue now. Sam,
Yes, ma'am. Thank you, Amna. Okay, so your diffraction is over.
Yes, sir.
Yes,
Okay,
sir.
fine. So the last topic in wave optics is interference. So let's start with interference now. Mr. Alhamdulillah. See, what is interference of light? Interference of light is just superposition of light waves from two sources. Let's say you have two bulbs. Light is coming from these two bulbs. The light waves from the two bulbs will superimpose each other and will give rise to a pattern which is known as interference. The superposition is very common. Like if you have two bulbs in your room, you switched on the first bulb, the light is coming from the first bulb only. Then you switched on the another second bulb, the light wave will come from both the bulbs. Then these two light waves will superimpose each other. They will combine with each other, and that particular superposition is what we call interference of light. But there is a slightly technicality in that superposition. The condition is the two sources from which the light waves is coming should be coherent sources. So superposition, you understand? Superposition means two waves combine to give a single wave. That is superposition. So if two light waves combine to form a single light wave, we call it as interference of light. But the light waves should come from two coherent sources. We'll see what are coherent sources. Now, this interference you can explain in terms of wavefront also. You did Heinz principle. Heinz principle says that light propagate in the form of wavefront. So in Heinz principle, according to Heinz theory, the superposition is the superposition of two wavefront gives interference. Interference is due to superposition of two wavefronts only. Now, the important thing about this interference is that light rays should come from two coherent sources. Now, let's see what do you mean by coherent sources. The coherent sources means if you have two sources and they are emitting light waves of same frequency, both the sources should emit wave of same frequency and a constant phase difference. These types of sources are known as coherent. So two sources which emit light waves of same frequency and a constant phase difference, then we call those sources as coherent sources. If we take two independent sources, Like if I take two bulbs, one bulb and another bulb, then by definition, these two bulbs can never be coherent. Like if you take two independent sources, then those two independent sources can never be coherent. To obtain a coherent source, what we can do is we can take light from a single bulb and divide this light wave into two parts. Then you get coherent sources. I'm repeating again. Coherent means if you have two sources which are emitting light waves of same frequency and a constant phase difference, then we say the sources are coherent. If you take two independent bulbs, then those two independent bulbs can never be coherent. If you want to make them coherent, take one bulb and somehow divide the light of this bulb into two parts. Then you can obtain the coherent sources. Note it down. Then we'll start Young's double slit experiment. I'll show you a small animation on this Young's double slit experiment. Then things would be very clear. What we know and what we are supposed to calculate. Yes, Shahzada, written?
Yes, sir.
It's okay. This is an important question. Explain interference on the basis of Heinz theory. It's just superposition of wavefronts from two coherent sources. Written, Sania? Sure. Now, before starting the calculation of Young's double slit experiment, I'm showing you an animation just to have an idea of what we are trying to calculate. What is the physical phenomena that we are trying to calculate? So this is a small animation. Where is the animation? That's it. Yeah. Yeah. Is it visible, this animation?
Yes, sir.
Yes, ma'am.
Yes, sir.
See, it's a very simple animation to understand Young's double slit experiment. So for Young's double slit experiment, Young's needed two coherent sources. So Mariam, can I take two bulb and call them as coherent sources? Two independent bulb, two mercury or two LED bulb, can I call them coherent? Fatma, can we take two independent sources and can call them coherent? Ahmad, you're not audible.
No, sir.
Why? Two independent sources can never be coherent, right? So to make a coherent source, you have to divide a single source into two. So see what Young's did. This is not sunlight or light coming from any bulb. He passed this light through a single slit. So this is a single slit. So this single slit will act as one source. This is a single slit. Slit means simply like you take a vertical piece and you make a hole into it. That's it. You take a cardboard and make a hole into it. That's a slit. Single slit means just one single hole. Double slit means two holes. So you take a slit with a single hole, it will act like a source, a single source. So light waves are these sunlights when pass through this single slit. When they pass through this single slit, this is S0. This is one single source. So light waves are coming from one single source. For interference, you need one source or at least two sources.
Two sources.
You need two sources for interference. Then what he did, he take a double slit pattern, means he take a cardboard, make two holes into it. And when this light will pass through it, it will divide it into two sources. See, when this light wave pass through this double slit, it gets divided into two independent, two sources. When it passes through it, yes. So it get divided into two sources. So light waves are coming from two sources. See, these two sources are not independent. These two sources are obtained from a single source only. So these two can be coherent sources. You can call them as coherent sources. Now, see, you can see these light waves. This light is coming from first source. This light is coming from second source. So light waves, see, this is the light which is coming from the first source. This is from the first source. And this light wave is coming from the second source. Now, what happens is, as they move forward, they get overlapped, they get superimposed. And as a result of superposition, you will obtain fringes. Fringes means patches. See, what happens is when these two light waves combine, at some point they gets added up, means light will add with light and brightness will increase. And at some points, light waves can cancel light waves. Now, this is not very common that we observe in our daily lives. What happens when you switch on one bulb and two bulbs together? What happens? The intensity of light increases or decreases?
Increase.
So when you switched on two bulbs simultaneously or two tube lights simultaneously, intensity of light increases. What happens is light wave get added up with the light wave. But what we are talking about is at some points, light wave will add up with the light wave. And at another point, light wave will cancel out the light wave. Light and light can get cancelled out. Well, the type of discussions we are doing means you switched on one bulb in your room, you get some brightness, some intensity of light. You switched on another bulb in the room, then if light of first bulb cancel out the light of second bulb, then you will get complete darkness. If you switch on one bulb, you have some intensity, some brightness in your room. But when I say that light cancel light, that means you switched on another bulb. And if that bulb can cancel the light of the first bulb, then you will get complete darkness in your room. This is the cancellation of light. But in day-to-day life, we don't see this cancellation. The reason is we don't have coherent sources. The sources we have are non-coherent sources. You can't observe interference in non-coherent sources. For interference, you need coherent sources. Okay, leave light waves. Let's come to sound waves. Have you heard about any device that can cancel sound? Have you heard about some sound cancelling and other sound cancellation devices? Okay. You haven't heard about the headphones which can cancel the
No,
background
headphone.
noises? Noise cancellation
Noise.
headphone?
Yes,
Yes,
headphone, yes.
The noise cancellation is very common nowadays. No? This Zoom
Yes.
offers noise cancellation.
yes, sir.
What does noise cancellation means? One sound wave will cancel out another sound wave. I'm using a headphone. This offers a really good sound cancellation. So what this headphone do is, if some external sound is coming through the headphone, this headphone will generate some sound which can cancel the external sound so that I can't hear any noise. This speaker is working on some noise cancellation. Like it takes only my voice, not any other voice. So it's canceling the other voices. This is noise cancellation. In sound, this is very common. We almost in day-to-day life, we use these noise cancellation devices. What these noise cancellation devices do, that one wave will cancel another wave. That's noise cancellation. Just like the way sound cancels sound, light cancel light. And this is what we want to study in interference. So when you take two coherent sources, what happens is in some region, light waves will cancel light wave and you will get darkness. In some regions, light wave will add with the light wave and you will get brightness. So if I let this.
Sir,
Yes, yes. Abdul.
so instead of using the screen with a single slit, we can directly use a screen with double slit, right?
Yes, we can use. I don't know why in this experiment he's using a single slit.
Okay, sir.
He's using single slit because he's showing sunlight, nothing else.
Okay, sir.
Yeah, so this is what you have to calculate. See, these are the bright spots and see, these are the dark spots. So in bright spots, Mariam, what is happening in the bright spot? Light is getting added up with the light phase or it gets cancelled out by the light wave? In bright spot, light add with the light or light cancel out with the light in the bright?
Add up.
Add up. And what about in the dark fringes, in the dark spots?
Cancel.
Light cancel the light. So in the bright spots, or we call them as bright fringes. We call them as bright fringes. And we call them as dark fringes. So in bright fringes, light will cancel, light waves get added up with the light wave. And in dark fringes, light waves will cancel the light waves. So this is the Young's double slit experiment that we are supposed to study. So what we have to derive mathematically? First of all, mathematically, we have to derive the conditions under which we get bright fringes and the conditions under which we get dark fringes. When you will get bright fringe and when you will get dark fringe, we have to derive those conditions first. The second thing is you have to calculate this thickness. You have to calculate this thickness of the bright fringe and the thickness of the dark. You have to calculate this thickness. You have to calculate the position of the bright and the dark fringe. One more thing. This is the central fringe. We call this as a central bright fringe. We will measure all distances from here. So in this derivation, in these calculations, what we have to calculate, we first have to calculate the conditions for which we get a bright fringe and the conditions under which we get a dark fringe. Second, we have to calculate the intensity of the bright fringe, like when you have a bright fringe, what is the formula to calculate the intensity of bright fringe, and you need formula for the intensity of dark fringes. Next, we will calculate the positions of the bright fringe and the dark fringes respectively, and where is the bright fringe, where is the dark fringe, and yes, the thickness of bright fringe and dark fringe. This is what we have to calculate. Yes, no. In interference, the width of all fringes are equal. But you did diffraction recently. In diffraction, your central bright fringe is the width of central bright fringe is maximum, and then width keep on decreasing. But in interference, the width of all bright fringes and all dark fringes is same. Intensity of all bright fringes and all dark fringes is same. Like Amna was explaining, okay, if phase difference is lambda, then why we get minima? When the phase difference is some lambda by 2 or 3 lambda by 2, why we get maximum? We have to derive those conditions, like when we get maximum, when we get minima in interference. Is it clear? This Young's double slit, this animation of Young's double slit experiment?
Yes, sir, it's clear.
Yes, sir.
Okay. There's another thing. See, the dark fringes, when we come to the real life, see, the dark fringes are not exactly dark. They are not black spots. They have comparative less intensity than the bright. Bright are very sharp, very bright points. they have intensity less than the bright spots. Then that's why we call them as a dark fringes. I mean, dark doesn't mean they are black. Dark means they have less intensity as compared to the bright fringes, and the intensity is significantly less. Like if bright fringes have intensity of 4i, that means dark fringes will have intensity of I by 4. So intensity is very, very less as compared to bright fringes. They are not comparable, but dark doesn't mean zero intensity. Okay, so let's take a screenshot and start our calculations here. Just one second. So that was experimental physics, and now this is theoretical physics. You have to derive the conditions under which you will get bright fringes and the conditions under which you will get the dark fringes in Young's double slit experiment. So this is your source. You put a double slit here. So this source get divided into two parts, S1 and S2. This is the screen. So waves will, these are the waves. When these waves move further, then they will superimpose each other, and due to superposition, you will get fringes over the screen. You will get bright and dark fringes over the screen. This is central bright fringe. So we'll get central bright, dark, and alternate fringes. Central bright, then you can get a dark fringe. Then you will get bright fringes and all. So in the first part of the derivation, you're supposed to calculate condition of a bright fringe and dark fringe. Condition for bright and dark fringe. Okay, but before starting this derivation, there's one thing which should be very clear in your mind, and that is the concept of phase difference and part difference. The whole of these calculations depends upon the phase difference and the part difference. So that phase difference and part difference should be very clear in your mind. So this phase and part difference you did in your class 10th, class 11th, that was in your class 11 syllabus. I'm repeating it again. See. First of all, understand what is phase difference. See, phase difference is a mathematical quantity. Like I can't show you phase physically. There's a mathematical quantity. Then there will come path difference. Path difference is a physical quantity. I can show you what this part difference is, but this phase difference is a mathematical quantity. Let's see how to calculate the phase difference. Say you have wave equation. This is the equation of wave, A sine omega t. This is wave equation of wave. Okay, before starting this wave equation, part difference and wave difference, I should discuss first the wave equation. See, the first thing is wave equation. This is the wave equation. Y is A sine omega t. In this wave equation, this y is the displacement. A is the amplitude. And this omega t is the phase. This is the wave equation. Y is the displacement of wave. Amplitude means maximum value of displacement. Maximum value of displacement. This you have already did in your EM waves. This we did in electromagnetic waves. This omega here is angular frequency. So it's not a new thing for you. We already did this in wave equation in electromagnetic waves. That's your wave equation, standard wave equation. Now, after standard wave equation, you're supposed to calculate the phase difference and the part difference. The next is phase difference. Then we will see part difference. Phase difference is something mathematical. So you have first equation of first wave, which is A sine omega t. And then you have equation of another wave. It's B sine omega t plus phi. Shahzada, let's check the phases of both the waves. What is the phase of the first wave? Shahzada, what's the phase of the first wave? Shahzada is, yes, he's in class. Shahzada, what is the phase of the first wave? Faisal, what's the phase of the first wave? The phase of the first wave is this omega t. This is the phase of the first wave. This angle is known as phase. Now, Faisal, what is the phase of the second wave? Fatima, phase of the second wave. It's okay, you can't unmute. Just give me 1 second. So can you unmute now? Good, Fatima. No. Faisal, you can do one thing like, okay, so this omega t plus phi, right, Fatima? This is the phase. No. Ahmed, what is the phase difference between the two? I need phase difference.
5.
Yes. So both the phases of both the waves are not same. They have a difference, and that difference is omega t plus phi minus omega t. So the phase difference is phi. This is the phase difference between two waves. So just by looking at the phase, you can decide what is the phase difference. Phase difference means it's difference in phase of the two waves. That's the phase difference. Phase difference is phi. So you should know wave equation before starting interference. Then you should know phase wave equation, phase difference, and the last thing that one should know is part difference. Path difference. So I'm giving you two sources. This is the source. This is S1. This is S2. This is the screen. So this is point P. So at this point P, light waves are coming from both the sources, from the source 1 as well as source 2. So the path that the first wave cover is x1, and the path that the second wave covered is x2. This is the path covered by the second wave. So Mariam, just look at the diagram. Which wave cover greater path? The wave from the source S1 or the wave from the source S2?
S2.
S2. Sania, what should, very good. So this x2 is greater than x1. This is path, huh? Path covered by the first wave. Oh, this is also the path which is covered by the second. So as you said, second wave covered greater path as compared to the first wave. What's the path difference, Mariam? How much should be the path difference? It's simple. The difference in path covered by the two waves, x2 minus x1, right? So that is the path difference, x2 minus x1. So path difference is simply the difference in path covered by the individual wave. So first wave covered a path of x1, second wave covered a path of x2. So the difference in these two paths is the path difference, x2 minus x1. Is it clear?
Yes, sir.
Yes, sir.
Okay, the last thing here, huh? After part, so you know wave equation, you know phase difference, you know part difference. Now the last thing is you should know the relation between phase difference and part difference. That is important. Relation between phase difference and part difference. So it's a simple relation. Delta x is lambda over 2 pi into phi. That is the relation between phase difference and part difference. Lambda is the wavelength of light. Phi is the phase difference. And your delta x is the path difference. See, although all these terms are not given in NCERT of class 12, but without these terms, you can't do interference. See, diffraction was not in very great detail. In your syllabus, this is introduction of diffraction. You didn't derive the equation for diffraction, but interference is in very, very, very detail. So you should know to do numericals and derivations of interference, you should know this difference. What is phase difference? What is part difference? And how you relate them. And this derivation is a 5-marker question from waves. Note it down. We'll do one or two numericals on it. Then we will start Young's double slit experiment. So the last topic of wave optics, polarization, Doppler's effect are not a part of syllabus now. In school, the syllabus is over.
Sir,
So
we
in the
started
last lesson-
semiconductors.
Semiconductors you are doing. That means it's over. Quantum physics is easy.
Sir, intrinsic and extrinsic semiconductors are there in syllabus?
Yeah, they are in syllabus. In fact, in semiconductors, only that much is left. Intrinsic, extrinsic, and that diode, some points.
Yes.
For the last few years, CBSE is decreasing the syllabus. Earlier, communication was also a part of syllabus, the last chapter of NCERT. And semiconductors was in very, very great detail, like the complete transformer was in syllabus, but now they have removed transistors as well. So you're left with intrinsic, extrinsic, PN junction, and diode. That's the syllabus. So this is the last topic which have some mathematics. After that, this whatever is left is very theoretical. Modern physics, semiconductor, theoretical topics. Can I scroll it?
Yes, sir.
Yes.
Written. Do this question now. So you have two wave equations. First one is y1 is a sine omega t, and second wave equation is y2 is b sine omega t plus pi by 4. These are two wave equations. Calculate. First part, phase difference. I need phase difference. Second part. Next, I need path difference. Yes, Faisal, can you unmute now? Okay. So it's a very simple question. We can do it together. So who will answer? Sania will answer. Sania, just look at these two equations. Can you decide what is the phase difference? Sania, she's not class. Fatma, what is the phase difference between these two wave equations, F1 and F2? Fatma, just look at these two equations. What is the phase difference between these two equations? Good, Noor. Yes, it's pi by 4. Very good. Just look at the phases. Nah, this is omega t, this is omega t plus pi by 4. So the difference is of pi by 4 only. So the first part, phase difference, I will represent by phi. It's pi by 4. Clear, Sania? Okay. Part difference. Now, you have phase difference. Now you're supposed to calculate part difference. So see, this is the relation between part difference and phase difference. I won't do the second part. Use this formula, get the value of part difference and write this in chat. Do it. You have phase difference phi, right? List lambda by 2 pi into phi. You know phi is pi by 4. Just do the calculation and write how much is the part difference. I need answer of each one of you. Shazada, just do these calculations. Good, Noor. Good, Abdullah. What about others? Ahmad, Fatma, Faisal. Write the part difference. I'll wait for 1 more minute only. See, we have already calculated phase difference. Now this is pi by 4. Just put the values phi equal to pi by 4 in this equation and get delta x. Mariam, what happened? No, Faisal. Faisal, you're making some mistakes, a small mistake. 5 won't be there. Good, Ahmed. Fine, 5 won't be there, Faisal. Fatma, Mariam, Sania. Good, Mariam. Correct answer. Sania and Fatma, your answers, please. Good, Faisal, it's correct now. Sania and Fatima. See, this is your part difference. Your part difference is good, Fatima. It's lambda by 2 pi into phase difference, right? So phase difference is pi by 4 now. So it's lambda by 2 pi into pi by 4. So this pi will cancel this pi, so we'll have lambda by 8. Okay, Faisal, it's not x, it's pi, so gets cancelled out. So your delta x is lambda by 2. Only Shahzada and Fatima haven't answered yet. Shahzada, is it clear up now? Lambda by 8? So for numericals, you should always know how to connect this phase difference and the part difference. Note it down. Okay. See, next, let's start with Young's double slit experiment. In Young's double slit experiment, the first thing is we need conditions for bright and dark fringes. We need conditions for which the fringe is bright and the condition for which fringe is dark. Condition means the values of phase difference and part difference. We need the value of phase difference and part difference for the fringes for which the fringe is bright, and the values of phase difference and part difference for which the fringe is dark. So we start with the wave equations. Let's say this is the first source. So the light wave coming from the first source, equation of light wave. Equation of wave from source S1 is, so this is the equation of wave from the first source. Y1 is A sine omega t. This is the equation of wave from the first source, first equation. Similarly, we can write equation of wave from the second source. Equation of wave from second source. Source S2 is Y2 is B sine omega t plus phi. That is second. See, what's the difference between these two waves? Both the waves have different amplitudes and they have a phase difference of phi. So I have equation of wave from this source. I have equation of wave from this source. Now I need equation of wave of this fringe when these two waves will superimpose. So the wave coming from this source and wave coming from this source, they will superimpose at this point. Now I need the equation of wave obtained after superposition. So for equation of resultant wave, we use superposition principle. Use superposition principle. So superposition principle is this, it's y1, it's y2. So when we put the values, y1 is a sine omega t, then this is b sine omega t plus phi. So this is the equation of resultant wave. Now we will do some mathematical manipulations just to put this in the standard wave equation. This is the standard wave equation, a sine omega t, b sine omega t plus phi. This is the wave which is obtained by the superposition of these two waves. These two waves combine to give this wave. So this wave should have the equation of the resultant wave. So you can write this as a sine omega t plus its b sine omega t cos phi plus sine phi cos. So you can write this as it's a sine omega t plus b sine omega t cos phi plus b sine phi cos omega t. Next, what we can do is we can take sine omega t common from these two. So I'm taking sine omega t common from here, and I'm left with a plus b cos phi. And then I can write this as cos omega t. I write this as b sine. Let's call this as equation number 3. This is the third equation. Next, what we can do is we can just put a plus b cos phi as r cos theta. And we write this b sine phi as r sine theta. See, this is the equation of resultant wave. This is the equation of resultant wave. Resultant wave means wave obtained after the superposition of two waves. But now we are trying to express it in terms of standard form. I'm using these variables just to express this in standard form. And what is the standard form? This is the standard form, either in a sine omega t or in b sine omega t plus phi, in this type of form. So here R is the amplitude of resultant wave. It's the amplitude of resultant wave. And theta is the phase constant. Theta is the phase constant. So I call this as equation number 4. I call this as equation number 5. Next we can substitute 4 and 5 and 3. So when we do this substitution, I will get y is its sine omega t. A plus b cos phi is r cos theta plus cos omega t. B sine phi is r sine theta. Next, we can take this r as common. I know it's a very dry derivation, but have to do it. This is a 5-marker question. Plus cos omega t sine theta. Next, this is the expansion of sine omega t plus theta. So you can write this as sine of omega t plus theta. This is the equation of resultant. This is the equation of resultant wave. So when I say resultant wave, that means wave obtained after superposition of two waves. See, this is the wave which is coming from source S1. This is the wave which is coming from source S2. When these two waves combine, you get this resultant wave. This is the resultant wave, the wave obtained by the superposition of two waves. And this is the equation of that resultant wave, r sine omega t plus phi. Do it and tell me wherever you have doubts. This is the second last derivative of your second last derivation of your class 12 syllabus. It's just one more derivation. After that, in modern physics, you have no derivation. In semiconductors, you don't have any derivation. Just fact, formula, that's it.
So is it in this chapter only or full
Your voice is not very clear. There's a lot of noise around here.
Sir, is it only for this chapter or for the full syllabus?
For this chapter only. For the remaining syllabus, I'm saying, see, in ray optics, we have already done all derivations. For the remaining part of the syllabus, for this interference, the next two chapters, modern physics, like atom, nuclei, radioactivity, and then in the last chapter, semiconductor. There is no derivation in the part of the syllabus that is left. Just two derivations in interference. In de Broglie hypothesis, you don't have any derivation. In photoelectric effect, you don't have any derivation. Written? Can I scroll it further? Yes, Abdullah. Can I scroll it? Equation 4. Noor, these are the substitutions. I'm using these variables r and theta by hand. And I know if I put this in terms of cos theta and I put this in terms of sine theta, then I will get the formula of sine omega t, sine a plus b type formula. So you have maths now?
Yes, I didn't take max.
You didn't take maths. Okay. So basically, these are the result of some back calculation. Like I know that sine of omega t plus theta is sine omega t cos theta plus cos omega t sine theta. This is the end result that I want. So I modify my equations in a way that I get this equation. So I put some this a plus b cos phi in terms of r and theta, and I put this a b sine phi and r sine theta. Just to get these equations in the standard form. That's why we are doing it. And there's one more reason for it. I want to get r, which is the amplitude of the resultant wave. See, the amplitude of first wave is A, amplitude of second wave is B. I don't know the amplitude of the resultant wave. I assume that this amplitude is R. Then in the next part of the calculation, we'll try to express this R in terms of phi, AB and phi. So I take these variables by hand. And why I take cos theta here, not sine theta here? The answer is I need a standard form is this form. And that standard form is possible only if I take sine and cos and cos and sine. That's why I take cos here and sine here. Can I scroll it further?
Yes, sir.
Yes, sir.
Sir.
Yes.
Sir, theta is phase.
Theta is the phase constant, not phase constant. Theta is the phase constant phi. For the first wave, your phase constant was 0. For second wave, it was 5. For the resultant wave, it's theta. Yes, written?
Yes, sir.
Now, next what we have to do, we have to relate. We need a relation between r, theta, r, AB and phi. So what we can do is square and add equation number 4 and 5. So we will square and add 4 and 5. So when we square and add these two equations, we get a plus b cos phi square, a plus b cos phi square, plus it's b sin phi whole square, which is r cos theta whole square, plus r sin theta whole square. So when you open the square, it's a square plus b square cos square phi plus 2ab cos phi plus b square sin square phi is r square cos square theta plus r square sin square theta. So see, b square cos square phi and b square sin square phi. B square is common. You can write this as a square plus b square. It's cos square phi plus sin square phi plus twice of ab cos phi. You can take r square as common. We have cos square theta plus sin square theta. So cos square phi plus sin square phi is 1. Cos square theta plus sin square theta is 1. So we have a square plus b square plus twice of ab cos phi is equal to r square. So you can write that your r is its root over a square plus b square plus twice of ab cos phi. So this is the relation that we need. What is r? Is the amplitude of the resultant wave. This is amplitude of resultant. And this is the amplitude of individual waves, and this is the phase difference. So the amplitude of resultant wave depends upon the amplitude of individual waves as well as phase difference. We can do one more. First, do this calculation. Tell me once you have written. So this is the relation on which you can get numericals. You'll get numericals on this relation. Amplitude of resultant. Yes, written.
Yes, sir.
Okay. See, after the amplitude of resultant wave, we also need intensity. See, what is the relation between intensity and amplitude? See, physically, we don't see amplitude, we see intensity. If I take a bulb of 100 watt and a bulb of 1000 watt, So the intensity of light coming from the 1000-watt bulb is greater than the light coming from the 100-watt bulb. So what we see, what we observe in real life is intensity, not the amplitude. But yes, the intensity depends upon the amplitude. So see how to get the relation between intensity and amplitude. I need intensity of wave from source S1, from first source, from source S1. See, for the first source S1, this is the first source. The wave coming from the first source is this A sine omega t. So the intensity of wave coming from the first source is I1, which is some constant k times square of amplitude. Let's call this as equation number 4, 5. This is 6. This is equation number 7. Similarly, intensity of wave from S2, source S2. The amplitude of wave from the source S2 was B. So the intensity of wave from source S2 will be KB square. Let's call this as equation number 8. Or you can say that root I1. If I take root on both the sides, you will write this as root K into A. Maybe you will need it somewhere. If I take root on both the sides, you will write root I2 is K root K into. Next, I need intensity of resultant wave. I need intensity of resultant wave. See, the intensity of resultant wave is K times the square of amplitude of resultant wave. The resultant wave is R. So the square of its amplitude is R square. You can write this as the square of this term. When you take square of this term, you are left with A square plus B square plus 2AB cos theta. Square plus B square plus 2AB cos theta. This is whole square of it. So I is Ka square plus Kb square plus 2AB. It's K into cos phi. So you can write this Ka square as I1. You can write this Kb square as I2. And see this A into root K, you can write as root I1. Then you can write it as root I2 and cos phi. So this is the relation between the intensity of the resultant wave and the intensity of individual waves. So these are the two relations which you will use in numericals. This one and this one. These are the two relations you will need in numericals. Note it down. Yes, the class is over. That was the last one.
Thank you, sir.
Sure. Okay, so we'll stop here. We'll continue this in the next class. So that's the last topic of wave optics. Huh? So hopefully we'll finish it in the next class.
Okay, sir.
So let's stop here. Hafiz. Okay, Sania.